just after midnight. Inside a mountain observatory, 3 scientists watch as their instruments fail. The measured length of metal rods, the mass of samples, and even the time between lightning flashes all produce contradictory readings. For centuries, global science functioned through a patchwork of isolated standards. Researchers in one region relied on centimeters and grams, while those a few hundred miles away used feet and pounds. We see the result of this disconnect here in this 19th century laboratory. Precision instruments sit scattered among tools calibrated to different local authorities. In this environment, a measurement of 5 units only worked within the specific borders where those units were defined. Sharing data across regions meant every calculation had to be manually translated and re-verified, creating a layer of friction that slowed the spread of new discoveries. To bridge these gaps, we have to look at the anatomy of a measurement. To quantify anything in the physical world, you need 2 distinct components working together. This diagram shows the split. You have the numerical magnitude, which tells you how much, and the unit, which tells you what kind. The localized systems of the past failed because the unit part of the equation was unstable. If the definition of a pound or a foot shifted from city to city, the number attached to it became impossible to trust. Humanity didn't just need a new list of names, we needed a unified architecture, a single set of definitions that would remain identical regardless of who was taking the measurement. This unified language is the International System of Units, or SI. It is the standardized framework that allows a scientist in one country to perfectly replicate the work of another. Early efforts to stabilize this language were literal. This marble plaque in Paris provided a public, physical standard for the meter, ensuring that the length of a single unit was visible and fixed for everyone in the city. Mass required even more protection. This metal cylinder, a historical standard for the kilogram, is kept under concentric glass bell jars to prevent dust or moisture from adding even a fraction of a milligram to its weight. This quest for precision led to 7 base units: meter, kilogram, second, Ampere, Kelvin, mole, and Candela. These irreducible blocks provide the minimum standards to define the physical world. From a chemical reaction's heat to a light's intensity, every phenomenon fits this foundation. These 7 units act as a trusted source code, allowing us to describe any complex event using a small, universal vocabulary. However, even with these 7 blocks in place, there was a remaining question: how do we categorize geometric angles? The system accounts for this with the radian, for angles on a flat surface, and the steradian, for solid 3D angles. They sit alongside the base units, but they are categorized as dimensionless. Unlike a kilogram of mass or a meter of length, these don't measure a physical substance. They describe the ratio between different parts of a circle or sphere, a spatial relationship rather than a physical object. These geometric units complete the structure, serving as the link between the physical blocks and the space they occupy. With only 7 base units, the system might seem limited. How can we use them to measure dynamic concepts like speed or force? We combine base blocks into derived units. Dividing a meter of length by a second of time merges them to define velocity. This stacking adds complexity. Combining mass, length, and time in a specific mathematical pyramid forms a Newton, the unit quantifying force. This modularity is the core of the SI system. It doesn't require a massive dictionary of separate rules. It simply requires the mastery of 7 building blocks and the math used to stack them. Because the world agreed on this single architectural standard, the friction of the past largely vanished. Calculations and data now flow between countries without the need for manual translation. This strict agreement ensures that a component manufactured in one hemisphere will fit perfectly into a machine designed in another, enabling the global scale of modern technology and trade. This rusted scale belongs to a world where measurement was a local, isolated opinion. Modern science moved past these crude tools in favor of a digital network of absolute precision. Universal acceptance gives the SI system its utility. It connects global industry and research through a single shared language. Returning to the storm at the observatory, the natural world can be loud and unpredictable, but it is no longer unmeasurable. When we use a shared foundational architecture, the data we collect becomes more than just a list of numbers. It becomes science. To see more deep dives into the foundations of physics and chemistry, like this video and subscribe to Science Knowledge.